Last one, 3-pin. How many different types of circuits can I make out of this? 3. We have what's called, I call a standard voltage regulator. It's still a regulator, isn't it?
Yes, sir.
We're just using an IC chip to act as the LM317 is the regulating element. It is. Because I told you to treat that chip just like the series pass transistor in the series voltage regulator. Because this right here is equivalent. Don't let this screw with you. In and out pin and out and adjust are 2 different things, aren't they?
Yes, sir.
You're not going to have the same readings. The out and adjust pin, you're always going to have that 1.25 volts, aren't you?
Yes, sir.
Because that's the program voltage. That's the output of the chip right there. That's that imaginary zener I've been drawing. Just imagine that. So therefore, I forgot to draw a component. R3, we call that the program resistor, don't we?
Yes, sir.
Standard voltage regulator. What's the other type?
0 volt.
0 volt. That's where we have to go over here and take this out. 2-post connector. Now, I didn't put one here, but imagine. Because we want this whole circuit in, or I could just take it out and leave it like that, couldn't I?
Yes, sir.
Yeah. So I need these components to get that 0 volt regulation. CR2 and CR3 are the diodes. They're in series with each other. When this is conducting, or when they are conducting, they're each going to drop about 0.6 volts or so to give me that negative 1.2 volts. Why is it negative? Because I have a negative 15 volt source here. R4 is just a current limiting resistor. I'm telling you right now, VR4 will drop about 13 volts and change. If you did the lab, you did it today, you should have remembered, hey, the brunt of the voltage drops here. Well, how much? What's the max voltage drop a diode can have anyway? 0.7 for silicon. It's not ever going to be more than that. If it is, something's wrong. So I need that negative 1.2 volts. This out and adjust pin is going to give me that 1.25, positive 1.25 volts, isn't it?
Yes, sir.
The diodes, R2, R3, aren't they in series?
Yes, sir.
If I have negative 1.2 volts and positive 1.25, what's additive in series?
Voltage.
If I algebraically add 1.25 and negative 1.2, what do I get?
Near 0.
Near 0. The load for the voltage regulators are what? Resistor.
5.
R5. What's the other type of regulator I could make?
Current regulator.
Current regulator. The load is R2. That's where I take R5 away. It's just R2. So we have to do something like this, put that back, because we don't need this part of the circuit. So now I have a series circuit here again. R2, R3, the chip itself, and R1. It's a series circuit. Current is the same. Not that whole circuit there, series, and I'm using current regulator, because R5 goes away. Take it away. R2 is the load this time. R2 is a variable resistor. By adjusting R2, its voltage drop is going to change, but the current is the same, isn't it?
Yes, sir.
This current's what in series? Common! Treat that chip just like the series voltage regulator transistor. The arrows are the same. The out and in pin are like the what of a transistor?
Like that.
Yeah, the VCE. It's like the VCE. Treat it as such. This is like the VCE. If you remember doing the lab, you placed your meter across the in and out pin, increased the line voltage. What happened across the in and out pin? It went up. It's the same thing. Here, I'm going to help you out. Line, load, in and out. It's like the what?
VCE.
The VCE. So line goes up, the voltage across the in and out pin do what? Increase. Decrease. In and out.
Yes, sir.
Decrease. What about the load?
Increase.
Same deal. Just like the series voltage regulator. Load goes up. Increase the load. Well, the circuit, the chip itself is now the regulating element, compensates for that. So the voltage across the in and out pin are going to increase, decrease respectively, just like the series voltage regulator. It's the same thing. Same. What does CR1 do in this circuit? What's it responsible for? CR1, right at the top of the chip. What's it do?
Protection.
Yes, reverse polarity protection, because it's placed in a circuit in reverse bias. If there is a reversal in polarity, or for some reason this becomes more negative, what's it going to do to that diode? What's it going to do to it? It's going to forward bias it. If it becomes more negative, isn't the cathode face the positive?
Yes, sir.
So it becomes more negative and forward bias to protect that integrated circuit. Bypassing it. R3, again, is called the program resistor, is it not?
Yes, sir.
R3 sets the what current? What's that called? Rhymes with program current. Program current! I sub P. Look. Program current equals what?
VR3 divided by R3.
VR3 divided by R3. VR3, do we know what that voltage is?
Yes.
What is it?
1.5 volts.
Why is it 1.25 volts?
It's in parallel with LM317.
Yes, because it's in parallel with the chip, the out in adjust pin. Out in adjust pin is constant. It's in parallel with R3, therefore VR3 must be 1.25 volts. And if I divide that by the value of R3, it's going to give me what's known as the program current. That program current, hey, R2 feels that same current because R2 and R3 are in series. How do we determine the output voltage for our voltage regulator? V out equals, if I put R5 back, probably VR5 equals, yeah, VR2 plus VR3. Doesn't that make sense? Isn't R3 and R2 in series? What's additive in series?
Voltage.
Let someone say current too. Voltage! We don't spend a lot of time talking about R1 because what does it do? What's its job? Yeah, it's a current limiting resistor. Current limiter, you could say. To what? The whole circuit, the chip. If I have the voltage regulator established, I've got R3, R2, R5. How many branches do I have for current? 2. So if I have the voltage regulator set up, the branch current, or you could say the program current branch plus the load branch equals total current. You can.